Globally, agricultural irrigation consumes more than 80% of our available fresh water. Feeding the planet requires an astonishing volume of water, and we are drawing it down at an unsustainable rate. As the climate shifts and fresh water becomes scarce, the survival of the agricultural industry depends on precision. Farmers need to move away from heavy blanket spraying and water their crops only exactly as much as they need. To do that, we need frequent, large-scale maps of soil moisture. The logical place to get that data is from orbit. But the optical and infrared satellites we usually rely on for Earth observation have a massive blind spot. Those sensors are easily blocked by clouds. Atmospheric particles like water droplets are larger than the wavelengths of visible light, causing the light to bounce off in all directions, a phenomenon known as non-selective scattering. The sensor only sees the bright white tops of the clouds. And even on perfectly clear days, visible light simply reflects off the leaves of the crop canopy. It can't penetrate the vegetation to see the actual dirt underneath. We cannot effectively manage our freshwater resources if our primary orbital monitoring tools are literally blind to the soil itself. This is where microwave remote sensing, or MRS, steps in to fill the gap. MRS systems operate in two different ways. Passive systems act like microphones, quietly listening for the faint natural microwave energy emitted by Earth. Active systems act like flashlights. They shoot a targeted radar pulse down at the ground and measure the energy that bounces back. Let's follow an active radar pulse. A satellite fires L-band microwave radiation toward Earth. With relatively long wavelengths, these microwaves aren't scattered by atmospheric water droplets, passing seamlessly through heavy cloud cover and slipping directly past the leaves and stalks of the vegetation canopy. By utilizing these specific frequencies, we have a remote sensing tool capable of reliably piercing both atmospheric and biological interference, allowing it to directly touch the bare Earth. When the microwave pulse hits, we encounter the dielectric constant. Dry soil is a poor conductor, but water is highly conductive. Wet soil acts like a mirror for microwaves, becoming highly reflective and bouncing a very strong radar signal back toward space. As seen in this academic text, the return signal isn't perfect. Rough fields and topography scatter microwave energy, amplifying backscatter and creating noise. Scientists must carefully calculate the incidence angle to mathematically filter out this interference from hills and rough terrain. Once the signal completes its round trip back to the orbital sensor, those calculations are applied. A highly robust radar backscatter signal definitively confirms a high soil moisture content. Isolating that precise moisture reading requires a massive physics calculation that strips away the physical noise of the terrain below. Scientists take this noise-filtered backscatter data and translate it into detailed, high-resolution maps of soil moisture. These moisture maps are then loaded into geographic information systems. This gives farmers an accurate digital overlay of their specific fields, showing them exactly where the ground is soaked and where it is bone dry. This data is then put to work on the ground. Modern agricultural equipment, like this tractor, uses variable rate technology linked to those GPS coordinates to navigate the farm. As the tractor drives across the field, it automatically adjusts its water and fertilizer output meter by meter. It applies heavy irrigation to the dry patches and shuts off entirely over the wet ones, all driven by data beamed down from orbit. By mastering the invisible physics of microwave backscatter, we can now regulate water consumption at the level of individual square meters, protecting global freshwater supplies from hundreds of miles in space.